Have you ever stopped to think about how life manages its most precious information? I mean, it's got to be stored somewhere, right? Well, it uses these two incredible molecules, DNA and RNA. And at a glance, they look almost identical. But here's the crazy part. One is like this permanent Fort Knox-level life's secrets, and the other is just a short-lived messenger. So how can that be? The reason for this huge division of labor? Well, it all comes down to a single atom. How can something so tiny have such a massive impact? Let's find out. Okay, so before we dive into the really deep molecular stuff, let's just do a super quick recap of what these two molecules actually do. It's this classic division of labor that's fundamental to, well, all known life, and understanding their different jobs is totally key to solving our mystery.
So you've got DNA. Think of it as the master blueprint, right? The stable, long-term archive of all our genetic instructions. RNA, on the other hand, is the go-between. It's the messenger that grabs those instructions and actually puts them to work. But this brings up a really interesting question. Why have two molecules at all? I mean, why couldn't DNA just do the messaging itself? Or why didn't life just stick with RNA, which seems pretty versatile?
To find the answer, we need to zoom in, like way, way in. The secret isn't actually in that famous double helix shape itself, but in the backbone that holds the whole thing together. And more specifically, we're going to focus on its central sugar scaffold.
Okay, so both DNA and RNA are polymers, which is really just a fancy way of saying they're long chains made of these repeating units called nucleotides. Now, each one of these nucleotides has three parts. You've got a phosphate group, a nitrogenous base, the A, T, C, or G you've probably heard about, and smack dab in the middle, a 5-carbon sugar. And that central sugar, that is where our entire story begins.
All right, we're getting warmer. We've zeroed in on the sugar component. Now, you got to prepare to be amazed by just how subtle, yet incredibly profound this difference actually is.
Look closely at that sugar ring. The entire story of why DNA is stable and RNA is reactive, why one stores information and the other just carries it, it all starts at this exact spot, right here. And there it is. Seriously, that's it. On the left, in RNA's ribose sugar, you see a hydroxyl group. That's an oxygen and a hydrogen, the OH, at what we call the 2' carbon position. Now look at the right, at DNA's sugar, that oxygen is just gone. There's only a hydrogen atom left, and that's exactly why it's called deoxyribose. It literally means without oxygen. This single atom is a smoking gun.
So okay, what does one missing little oxygen atom actually do? Well, its first effect is dramatic. It completely changes the molecule's three-dimensional shape, all through something called a sugar pucker.
See, a flat, 5-sided ring like this one would have a ton of internal tension, or what chemists call steric strain, because all the atoms are just too crowded. So to get more comfortable and stable, the ring actually bends, or puckers, into a 3D shape. It kind of looks like an open envelope. 4 of the atoms stay flat while the 5th one pops out. This little pucker is absolutely fundamental to the final shape of both DNA and RNA. Now, let's see how this plays out. In RNA, that bulky hydroxyl group creates a steric clash. It's basically bumping into its neighbors. To make some room, the ring is forced into this specific shape called a C3 endo pucker. But in DNA, without that bulky group in the way, the ring is totally free to relax into a different, much more favorable shape, the C2' endo pucker. And this tiny change in shape is what lets DNA form that elegant, super stable B-Form double helix that we all know and love. Changing the shape is a huge deal, for sure. But that single oxygen atom has an even more profound chemical consequence. It's literally the difference between a molecule being built to last for centuries and one that's built to self-destruct in a matter of minutes.
So here's the crucial point. That oxygen in RNA's hydroxyl group is chemically reactive. It's what's called a nucleophile, meaning it's always looking to attack positive charges. And under the right conditions, it can actually attack its own phosphate backbone, which causes the entire RNA chain to just snap in two. It's wild. RNA basically carries the seeds of its own destruction.
The result of all this is crystal clear. RNA is like a chain with a built-in weak link, making it super vulnerable and temporary, which, by the way, is perfect for a message you don't want sticking around forever. DNA, on the other hand, by simply not having that reactive oxygen, is like a solid, stable rod. It's incredibly robust and resistant to this kind of breakdown, which is exactly what you want for a long-term information archive.
So let's connect all the dots, right? The absence of that one oxygen atom gives DNA both structural integrity, allowing for that stable B-form helix,
and chemical stability, making it super resistant to breaking down. This powerful 1-2 punch is precisely why evolution chose DNA and not the much more fragile RNA to be the primary keeper of the genetic code.
It really is an incredible story of cause and effect, isn't it? A single, tiny change at the atomic level just cascades upwards, defining the shape, the stability, and ultimately the entire destiny of each of these molecules.
And this table just brings it all together beautifully. You can see the whole chain of logic laid out right here. It all starts with a sugar, deoxyribose for DNA, ribose for RNA. That one difference at the 2-carbon dictates the pucker, which then shapes the helix, which then determines the stability. And that, at the very end of the chain, is what gives these two molecules their completely different jobs in life. One as a permanent archive, the other as a fleeting messenger.
When you get right down to it, the divergence of DNA and RNA is just a masterclass in molecular logic. A minimal change, literally removing a single oxygen atom, gets amplified to create two molecules with profoundly different destinies. One is built for permanence, a stable library holding life's deepest secrets. The other is built for action, a dynamic messenger that brings all those secrets to life. Understanding this distinction isn't just a tiny detail. It's fundamental to understanding biology itself.